Okay. So before beginning to our next session, I hope you all have taken your lunch and are back with us with same energy as you were having in the morning. So this session, as I also previously mentioned, will be delivered by Major Dr. C.S. Sanghvi sir on the topic of earthquake basics, concepts of earthquake resistant design, and challenges in India and design assignment. But before that, I would like to take few moments to introduce the dignitary, because in the morning session, as we were hurrying in the time, I didn't introduce well. So I would like to grab this opportunity now. So Major Dr. C.S. Sanghvi sir, the professor head and of Applied Mechanics Department, Government of Engineering College, Modasa. Sir completed his bachelor's and master's from Gujarat University and has completed his PhD from SBNIT School. He has a professional experience of more than 30 years and has presented numerous technical papers in national conference, international journals, and has also published various books on technical subjects. We have a unique in-house earthquake engineering laboratory, as I mentioned in the morning session as well, at LD College of Engineering, which was established under the leadership of Sanghvi sir. Sir has prepared 18 episodes on earthquake resistant construction for the civil engineering professionals, which had been telecasted on DD National Network. He has conducted and coordinated training programs in the field of earthquake engineering for Class 1 and Class 2 officers of state government at Sardar Patel Institute of Public Administration, SPIPA. He has also coordinated various training programs along with IITs. Sir is actively associated with NCC and NSS activities in the state, and many students under his leadership are taking part in Republic Day Parade and have received awards at national level. Sir has received the National Award for Best Program Officer of National Service Scheme by President of India, Sri Ramnath Kovind. Now, this list will go unending, but we all have gathered here to listen from Sir, the dignitary himself, on the confined machinery topic. So I won't take another extra moment further, and I'd like to hand over the dais to Sanghvi sir. Over to you, sir.
Thank you, Aditya. Uh, so welcome to the post-lunch session, and we try to interact in this session because after lunch, always it's difficult to attend. Session is very difficult. So I'm sharing my screen right now, and can you see my screen?
Yes, sir. Yes, sir.
Yes. Okay. Thank you. So in the morning, I told you that the design of confined masonry building for earthquake disaster risk mitigation in India. This is the first training program after the development of the confined masonry code, and uh, it is our pleasure that we are conducting this training program. And today's my topic is earthquake basics, concept of earthquake resistant design and challenges in India. So we'll discuss uh, uh, some basic parts of earthquakes, and then we switch over to the concept of earthquake resistant design, and then we discuss the challenges what we are facing in India. So this routinely I start my session with this only, and we talk about the various disasters. We talk about the earthquake, and we have seen loss of life as well as the economic loss. You can see here the buildings are collapsing. You can see once a person is losing his house, that is the cyclone. We have a flood. We talk about the fire, landslide. We talk about the liquefaction. We talk about the tsunami and many other disasters, right? But these are the disasters which are important from the structural engineering point of view. So these disasters are included here. And when we talk about these disasters, either we are categorizing this disaster into the natural disaster or man-made disaster. And most of the time, we are saying that earthquake disaster is a natural disaster. Cyclone, we say it's a natural disaster. Flood, when it comes to flood, we are saying that it is a both way. It is a natural disaster as well as a man-made disaster. Because sometimes, because of the mistake of the human being, the area is flooded. For example, what happened in Surat was the classical case of man-made flood. Same way, Machu Dam was collapsed way back in 1978, and that was because of the human error. So you can say it's a man-made disaster. Uh, so flood may be man-made, it may be natural. Same way, fire is also natural and man-made. Landslide, again, it is a natural and man-made. For example, if landslide triggers because of the earthquake, which is natural, but uh, once you carry out the mining operations in hilly region, and if landslide triggers because of the explosion you are doing in the hilly region, then it is a man-made landslide. Same way, you have a liquefaction and the tsunami. The tsunami generally we categorize into the natural disaster. Right. Now, you see, when I'm saying the natural disaster means nature is angry, right? Uh, at that particular moment, you are not going to approach the nature, right? Suppose we consider a very hypothetical case of cyclone. Suppose a cyclone hit uh, right now, then exactly what will do? Uh, you are in your office, or you are in your home, right? So you will try to remain in your home or the office, because the cyclone is a natural disaster, and at that particular moment you are not going to approach the nature. You don't want to try to come out of your house or your building, right? Because nature is angry and you do not want to approach the nature at that moment. But if you talk about the earthquake disaster, for example, now when earthquake comes suddenly, for example, right now, then what you will do? Am I audible?
Yes, sir.
Yeah, okay. Now, if I'm talking about the earthquake, for example, if earthquake hit uh, uh, the particular region, then what you will do? We try to go out of the building, right? We try to go out of the building and we try to go to the, where will we go? We try to go to the open space, right? And what is open space? Open space is a nature. So when earthquake strikes, at that particular moment, you try to come out of your building and you go to the open space, which is the nature. So you are approaching nature at that particular moment. During cyclone, you are not approaching nature, but during earthquake, you are approaching nature, right? Why? What is the reason? The reason is we don't have faith in our building. We don't have faith in our building because we are not sure whether our buildings are safe from earthquake point of view or not. And therefore, we feel that building will collapse and the casualty may happen. So therefore, we are running out of our buildings during earthquake. Right now, who built this building? That is important. We human being has built this building, and uh, it collapses because of the human error. And therefore, we are always saying that earthquakes do not kill, but the unsafe buildings do. Right? This is very important. You have to understand this. This is a challenge number one. I am saying earthquakes do not kill, but the unsafe buildings do. Therefore, I am saying that earthquake is a man-made disaster, and therefore the solution lies in the building, not in the earthquakes. You have to make your building safe, right? You have to consider all types of earthquakes, right? When you design your buildings, but your building should remain safe during the earthquake. That is the most important challenge we have, right? So you have to focus on the building safety. You have to construct a building in such a way that it remains safe during earthquake or any disaster, right? So again, I'm saying earthquake do not kill, unsafe buildings do, and therefore earthquake considered to be a man-made disaster. Earthquake is a natural hazard, but it is the disaster is man-made. If you look at any particular disaster, then you find that two things are right. The loss of life. Patriotism is loss of life. If I say 100 people die during the disaster, out of the 147 die in earthquake. So highest contribution is coming from the earthquake. Same way, if we lose 100 rupees, then out of this 35 rupees is the contribution of earthquake. Highest economic loss, which is also associated uh, because of the earthquake, right? So you have to be very cautious when you're dealing with the earthquakes and the structures. Right. So earthquake so design of buildings for earthquake is a very challenging job. So we go to the scenario of Indian earthquakes. Right. We are knowing that uh, uh, there are 7 major tectonic plates. Right. Eurasian, Indo-Australian, Pacific plate, North American, South American, African, and Antarctic plate. But uh, if you look at the India is somewhere here, right? India is somewhere here. So India is basically located on the boundary of the two plate, Eurasian plate and Indo-Australian plate, right? And the Indo-Australian plate is going below the Eurasian plate. Indo-Australian plate is going below the Eurasian plate, right? We are knowing that on the northern boundary right now we are observing Himalaya there, but 10 crore years back there was a sea, and this sea was disappearing. This Indo-Australian plate is moving below the Eurasian plate, so they are creating pressure on each other. And you see what happened at one moment when the stresses within the plate exceeding the limit, then this plate will break, and therefore the majority of earthquakes are coming on this boundary of these two plates, right? So if any earthquake which is taken place on the boundary, which is known as an interplate earthquake, and the earthquake which is taken place within the plate, it is known as an intraplate earthquake, right? Now if you look at this, we have seen this picture, right? This is the boundary of Indo-Australian plate and Eurasian plate. This is the boundary where these two plates are interacting. The Indo-Australian plate is going below the Eurasian plate, and therefore you can see the more than 95% earthquakes are coming on this boundary, right, where these two plates are interacting. 98% earthquakes are coming on this boundary, right? This is the epicentral map. So when we are locating earthquakes on a map, or epicenter of earthquakes on a map, it is known as epicentral map, and this map will tell you that most of the earthquakes are coming on the boundary of the two plate, and within the plate few earthquakes are there. So almost 98% earthquakes are on the boundary, and maybe 2% earthquakes are within the boundary of the two plate, right? So this is very important for us to understand that most of the earthquakes are coming on the boundary of the two plate. And this is a seismic zone map of India. If you look at this, then you find that we are knowing that here the two plates are interacting, and therefore this region where two plates are interacting, right? Now if you look at this, the whole India is divided into 4 seismic zones. So zone 2, 3, 4 and 5, right? Now zone 2 is having the least seismic risk, and zone 5 is having the highest seismic risk. And if you look at the seismic zone map of India, you find that North India or Northeast India, it is actually divided into either zone 4 or zone 5. So the North India and Northeast India is having the highest seismic risk as far as India is concerned. And if you look at the Gujarat, then in Gujarat also the red color is there. The red color means is always a danger, and it is zone 5, having the highest seismic risk. So this is not on the boundary of the two plate, and even though this area is marked with the red color, zone 5, the reason is that the Kutch region of Gujarat is very active as far as earthquakes are concerned. The faults which are existing there, they are very active, and therefore the Bhuj region or Kutch region of the Gujarat is having the very high potential of big earthquakes, right? And we have seen in the past also, we have a big earthquake in 1819, and we have a big earthquake in 2001 also. So these are the some big earthquakes located on the map of India. You can see here there is a 1897 Assam earthquake, right? A big earthquake whose magnitude is more than 8. Then we have a 1905 Kangra earthquake. Then we have a earthquake of 1934 Bihar, Nepal. It is located somewhere here. And then 1950 again, it is Assam, which is located here, right? So, and this is the 2001 Bhuj earthquake. So these are some important earthquakes of India, which is displayed on map of India. And you see, this is the epicenter where the Bhuj earthquake was taken place, right? This is the place where the Bhuj earthquake was taken place. Now, if you look at some past Indian earthquakes, and if you look at this particular list, then you find that the Kutch earthquake of 1819 magnitude is 8.3, right? And the number of deaths observed is 1500. You see, in 1819 it was thinly populated, and even though 1500 deaths had been observed, and if you look at the Assam earthquake of 1897, it is 8.7 and 1500 deaths again observed. Right? If you look at the Coimbatore earthquake, 6 magnitude, but the most important thing is this number. No death had been observed during the Coimbatore earthquake. Now, Coimbatore is in the south. It is an intraplate earthquake, and magnitude was less, and the time of shaking was also very less. The Kangra earthquake of 1905, 8.6, 19,000 deaths had been observed. Just imagine, in 1905, Kangra is in Himachal Pradesh, and if such a big numbers of casualty happen during that time, it exhibits the severity of that particular earthquake. We have a Bihar Nepal earthquake of 8.4 magnitude in 1934, 11,000 deaths, and the Quetta generally right now it is in Pakistan, so we are not talking about the Quetta earthquake, but earlier in 1935 it was a part of India. The earthquake was 7.6 and 30,000 deaths. I mean, this is the earthquake in which highest reported death had been observed. And 1950 Assam, 8.5 again, right? So we have so many earthquakes whose magnitude is more than 8, right? We have a 1956 Anjar earthquake, 1967 Koina earthquake. This Koina earthquake, Koina is in Maharashtra, and this earthquake, we believe that it came because of the reservoir, large reservoir, and so therefore the Koina earthquake is known for the reservoir-induced earthquake, right? Then we have a Bharuch earthquake of 1970. Now you look at 1988 onwards, right? So I'm just skipping this slide, but importantly, observation is Bhuj earthquake. In Bhuj earthquake came on 2001, and magnitude was 7.7, and 13,805 people died. Right. So this is something unusual thing happened. Right. Numbers of deaths are. It should be nil. Again, I'm saying we always assume that our structures are safe. We design our structures in such a way that it should remain safe during all disasters, and therefore this number should appear nil as far as the column of death is concerned. But you can see 14,000 deaths within a few seconds, which is something amazing, right? So if we talk about some great Indian earthquakes, I told you that India is having uh, probability of having big earthquakes. Whose magnitude is 8.3, means the magnitude is more than 8. It is considered to be the great earthquake. So India has observed 5 great earthquakes in past: 1819 Kutch earthquake, 1897 Assam, 1905 Kangra, 1934 Bihar, Nepal, and 1950 Assam. Out of this, if you look at this, these 4 earthquakes are interplate earthquakes, and this earthquake is only intraplate earthquake. So I'm talking about the earthquake which are taken place on the north or northeast boundary, right? I'm talking about this. So if I'm talking about the interplate earthquake, then you will find that the 4 earthquakes from 1897 to 1950, means how many years? 53 years. India has observed 4 great earthquakes. What is the written period? The written period is 13 years, right? So we can conclude that the India is having a probability of having big earthquakes at the interval of 13 years. This you see, the whole earthquake engineering is based on probability. You can see this the last 72 years, from 1952 to 2022, no great earthquake was taken place on the boundary of these 2 plates, right? But if I'm saying that the India is having the probability of having big earthquakes at a regular interval of 13 years in past, this is what we observe, then I can say that after 13 years we have a probability of having big earthquake. If it is not coming, then again after 20 years the probability will increase. Now you can see 72 years it is already gone past, right? And we don't have a great earthquake on the boundary of these 2 plates, right? And therefore there is a theory of seismic gaps. There is a theory of seismic gaps, right? If you look at the theory of seismic gap, that uh, this if you look at this figure, the red color is actually significant earthquakes which happened in the North India or Northeast India, and they are located on a map. Now the red indicates a big earthquakes in this particular region. But you see, the some regions, for example, it is marked with the blue line. This region, there are there are no earthquakes, no big earthquakes observed in this particular region, right? So the whole plate is moving, so the pressure is built up, the stresses are built up in these 2 plates, and the theory of seismic gaps is saying that if no earthquake is taken place in this region, the blue region, it means the lot of stress has been built up there, right? It already, the stress is built up, and therefore there is a possibility that next big earthquake may come in this particular region, right? Next big earthquake will come in this particular region. So we have to be very careful, and we must have a very proactive approach to deal with such natural hazards. The challenge too is that in India, a regular occurrence of major earthquakes are happening, right? I told you that in 1988 we have a Bihar, Nepal. After 3 years we have a earthquake in Uttarkashi. Then 93 in Latur, 7 Jabalpur, 2001 Bhuj, 5 Kashmir, 11 Sikkim, 15 Nepal, right? So consistently, if you look at the pattern, after 2, 3, 4, 5 years, the major earthquakes are coming in this particular region, right? So it is always a challenge for us. We have to uh, um, go in such a way that we can uh, uh, create a building which are earthquake resistant, right? They can resist this earthquake in this particular region, northeast, and the uh, other seismic zones where a possibly big earthquakes are there, right? So the challenge 3 is the structural engineering challenge, right? When we talk about the our structures, we are generally designing our structures for the loads acting on it, right? And there are two types of loads: the gravity loads, which are acting in the direction of the gravity. They are dead load, live load, right? And some of the loads which are acting in the lateral direction, right? I'm talking about there are so many types of loads are acting on your structure, but I'm talking about the basic loads of concern for which we are designing our structures. So I'm talking about the dead load and live load, which are acting in the direction of gravity. They are known as the gravity loads. So generally this load is acting on your structure, so we consider it to be a permanent load. And then we are knowing that if I'm designing my column for 100 kilonewton, then I'm applying the factor of safety of 1.5 load factor we are applying, and when I'm designing that column for 150 kilonewton, right? So actual load coming on that column is 100. We are designing for 150. It means your structural element is not going to damage under any circumstances, right? So they are designed for no damage condition. This is very important, right? When you're designing your structure for gravity loads, it is designed for no damage condition, right? So this philosophy of designing element for gravity loads, it is not allowing any sort of damage because the factor of safety is involved. When I'm talking about the lateral loads, then definitely wind and earthquake is going to come in our mind. The wind is quite frequent, and when we design our building for the wind force, we are designing the factor of safety, and we are not allowing damage during the wind force, right? During the cyclone, we are not expecting damage because we are designing our structure with a factor of safety. But when it comes to earthquake, right? When it comes to earthquake, how we design, that is important. Now, if you look at the earthquake event, because you see, to understand the philosophy for earthquake design is something different as compared to the design philosophy for the gravity load. So we have to understand earthquake first, right? Actually, what happened in the earthquake? In earthquake, the rock will fracture, right? And uh, because of the sudden fracture of a rock, energy will released, and this energy will travel in form of waves, and these waves will shake the foundation of the building. So some of the energy is entering into the building, right? And your building has to absorb this energy, right? And if your building is able to absorb this energy, your building remains safe. And if your building is not able to absorb the energy, your building will collapse. And if you look at the for how much time your structure is subjected to earthquake force, and if you look at the uh, the the earthquake uh, history, earthquake time history, if you look at the acceleration versus time, then uh, the maximum effective time of earthquake shaking is 2 minutes, right? 2 minutes, and within 2 minutes, this earthquake is going to check all the buildings which comes under his way, right? So that is the power of nature. So within 2 minutes, the buildings will be checked whether it's designed properly or not, right? So uh, uh, when I'm talking about the earthquake, then I'm not sure whether my building will absorb earthquake or not, right? We'll see that part. So that's why I had taken this example. Compare two structures constructed in Kutch region of Gujarat, right? Uh, Generally, the buildings are designed for 50 years, right? Right now, in Gujarat, the construction of tall structure is allowed, and as per the code, most of the tall structures whose height is more than 100 meter, they are designed only for the 50 years. Here I am considering 100 years, right? So it is double what is mentioned in the code. I'm considering the life of the structure is 100 years, right? Now, uh, uh, I'm considering the first structure, which is constructed in 1818, right? 1818. And if I consider the life of the structure is 100 years, life of the structure 100 years means, you see, you understand, for these 100 years, your structure should remain functional. The stresses must be within limit, right? Then and then you can say that your structure is fulfilling the requirement, uh, right? So your structure should remain functional, and the stresses must remain within the limit. That is the requirement uh, uh, for structure to be usable, right? So now I'm considering the first building, which is constructed in 1818, right? Now if I consider life is 100 years, means it expired in 1918, right? Now we are knowing that there was a great earthquake in 1819. So this building has observed a great earthquake in 1819. So it was constructed in 1818, and in 1819 it has observed a great earthquake. And if we can learn from this building, then we understand that we have to go for the earthquake proof design. We have to design in such a way that no damage should occur. So when we design for earthquake proof, design the building as earthquake proof, then it is always safe, but it is uneconomical. It is uneconomical, right? Now I'm considering considering the second structure, which is constructed in 1820, right? Second building 1820. Now this building will expire in 1920, right? So if you look at the history of earthquakes in Kutch region, we had a great earthquake in 1819, and then we have a major earthquake in 1956 in Anjar, right? Now if I'm talking about this building from 1820 to 1920, then this building has not observed any earthquake. Now this is the another part. One building has seen earthquake after its construction. The another building has not seen any earthquake during its life. So therefore we are saying the earthquake is not a sure event, right? Earthquake is not a sure event. Whether your building will see earthquake during the life or not, it is not sure, right? And if we learn something from this building, the second building, which is constructed in 1820, then this building is saying that there is no need to design for earthquake, right? Now you see, I told you that whole earthquake engineering is based on probability. And if the next, suppose the earthquake came in not in 1820 and it came in 1850, then it will observe, it might have observed collapse, right? So the building become unsafe. And for unsafe buildings, uh, there is no space in the field of construction, right? So we cannot design unsafe buildings, right? So the first building is saying that you design is at a designed the building as earthquake proof, and this building is saying that there is no need to design the building. So two extremities, right? And therefore what we can conclude that earthquake event is not a sure event, right? Earthquake event is not a sure event, and therefore we are going for the another approach, which is known as earthquake resistant design. Now what is earthquake resistant design? That I'll tell you, right? Now this earthquake resistant design, we are allowing the damage, but we are not allowing collapse. So when I'm allowing the damage in my structure, uh, but I'm not allowing any sort of collapse, then it is safe, right? So your building is not going to collapse during the earthquake, so it is safe. And at the same time, it is also economical, because I am designing my building for a lower level of the force, right? So instead of going for earthquake proof design or no design concept, we are going for earthquake resistant design concept, right? And this is the only philosophy in which damage is expected. Now I will make you understand what exactly we are doing in earthquake proof design, right? So here you look, this is the uh, uh, this is a point B. This is the maximum force coming on your structure, right? And when I'm designing my structure for this force, maximum force, right? And this is the force versus deformation curve, force versus deformation curve, right? Now it remain a linear means this remain elastic, it remain elastic, right? So when I'm designing for the maximum force, and during this my structure remain elastic, it remain elastic, then it is not going to observe any damage, because we are knowing that the structure will deform and then it will come back to original position without any sort of damage, right? So your building is safe, but you are designing, for example, this is 100 kilonewton, for example, this load is 100 kilonewton. When you are designing for 100 kilonewton, you it your your structural element will become too costly, it will become uneconomical, right? So it is safe but it is uneconomical, right? And we are knowing that earthquake is not a sure event. Earthquake is not a sure event. So whether this building will see earthquake or not, so if you are going to invest so much here, then it may create a problem, right? So it is not economical. But the important thing is, as the load deformation curve is a linear, and therefore ductility is not required in this. Now we take the second case. The second case, what we are doing, we are assuming that we are saying that earthquake event is not a sure event. So we are going for the another approach, is resistant design. What is earthquake resistant design? I am knowing that okay, the maximum load coming on your structure is 100, right? 100. But I do not want to design for 100. I only want to design for 20, maybe 20, maybe 30 kilonewton, right? 20% force. That's all. I want to design for that. Now, instead of designing your structure for 100 kilonewton, if you are designed for only 20, then definitely the size of your structural element will come down, right? So definitely your structure will become economical. But the question is, when you design your structure for 20 kilonewton, whether your building will survive during the earthquake or not? That is the question, big question. And therefore, you see, you have to look at this part only, right? This is the another way we are designing our structure, right? So what we do here, we are not designing for 100, we are designing for 20, right? Now here we are restricting the load, but we have two parameters, load and deformation. Here we are playing with the deformation, right? We are saying that I'm allowing my structure to deform more than what I'm expecting in the previous concept. For example, here in this case, what is happening? Earthquake proof design, I'm designing for 100, and your load deformation curve is a linear, and this area under the curve, basically area under the curve is, it will give you what? Work done. It is the work done. Work done means energy absorbed by your building. So you see, you have to understand that during earthquake, energy released, right? Energy is released during the earthquake, and your building has to absorb this energy, right? Building has to absorb this energy. It means this much energy your building has to absorb. And here, for the second concept, what I'm doing is, I'm assuming that earthquake event is not a sure event. I am playing with the either load or the deformation. So in this concept, I am playing with the deformation. So what I'm doing, I'm designing for 20. So it is designed up to this level only. Remember, it is designed for only this level, right? 20 only. But here, from this, I'm allowing a deformation in this direction, right? Larger deformation. So up to this, your structure remain elastic, right? Here, this is the region where your structure remain elastic, and then it enters into an inelastic range. So this is the inelastic range, remember, right? Now the important thing is the area under the curve. Area under the curve is important for us, because that is the energy absorbed by the structure, right? So here in the previous case, this is a triangular portion, and this is the amount of energy absorbed by the structure. The same amount of energy is absorbed here, right? But here we are allowing our structure into structure to enter into inelastic region, right? Now this is the particular point. This point onwards, this is the inelastic deformation. Remember, this is inelastic deformation. And if this is inelastic deformation, then what is the meaning of it? If your structure is entering into inelastic deformation, means it is a permanent deformation. If it is permanent deformation, means there is a damage, right? So from this point onwards, damage starts. It means we are allowing the damage in our structure, right? We are allowing damage in the structure. And here comes the ductility part, right? Ductility part. What is the ductility? The ductility means capacity to undergo large inelastic deformation after yielding without losing strength and stiffness, right? So here, this is basically this is the ductility we are talking about, right? We are saying that your structure should be ductile, right? It should be ductile, and this is the ductility we are talking about, right? We are talking about the ductility, remember. And for this we have a IS code, IS 13920, right? So here we are allowing this inelastic deformation. Remember this inelastic deformation. So this earthquake resistant design, we are allowing the damage. Right? So here the damage is allowed. This particular portion damage is allowed, right? But no collapse. Remember, no collapse. So it is safe. Because no collapse is observed, and it is economical because instead of 100 you are designing for 20. So your structure elements are very small as compared to 100, right? So here you are designing for only 20% force. But only risk in earthquake resistant design is if earthquake comes, then you have to be ready for the retrofitting. Right? So in case of a major earthquake, sorry. So in case of a major earthquake, your building will absorb damage, and there is a possibility that retrofitting is needed after the earthquake, right? So therefore, I'm always saying that earthquake is not a strength-based design. We are not designing for 100% strength. We are designing for 20% strength. But the earthquake resistant design is basically based on energy absorption concept. Energy absorption, right? How much energy absorbed by your structure? Because earthquake releases the energy, and your structure has to absorb the energy, right? Here we are allowing the damage. Remember, we are allowing the damage. We are making our structure ductile, and when we make our structure ductile, then it will absorb a lot of energy. So you see, earthquake resistant design is always a challenge. Why it is a challenge? Because actual load coming on your structure is 100 kN. You are designing for 20, and after designing for 20, you are still saying that my structure is safe. Now just compare with the dead load and live load design. Actual load coming because of the dead load and live load is 100 kN. You are multiplying with 1.5, and you are designing for 150, right? So when you design a column for 150 and actual load coming on the column is 100, definitely your structure will not going to observe any damage. Your column is not going to observe any damage. But in case of earthquake, actual load coming on your column is 100. You are designing for 20 kN, only 20% force, and still you are saying that my structure is safe. So that is the challenge, right? So earthquake resistant design is a challenge, and as a engineer, we have to contribute to make our structure safe, right? Now there are various challenges we have ahead. We'll discuss that part, right? Now here, this is very important. Remember this curve. So this is the maximum load which is coming on your structure because of the earthquake, and you are designing here only for this much force, right? So here, this is the design force, and you see how you are reducing. Why you are reducing this maximum load to this design load? This is because of the ductility. This is because of the redundancy and the overstrength. These are the three factors on which we are depending, and we are reducing this load, right, from maximum load to the design load, right? So here you can see we are designing in such a way that it your structure should behave in a ductile way, and it will absorb a lot of energy. Again, I'm saying during earthquake you have to design your structure in such a way that it should absorb maximum energy, because during earthquake energy will release, and this energy is actually entering into our building, and our building has to absorb the energy to make our structure safe, right? So up to this particular point your behavior is elastic, and then onwards you have inelastic behavior. So that is the you can say uh, uh, ductility will come in picture, right? So if you look at this, then you find that this a blue curve will tell you a ductile performance, and the brittle performance means this building collapse because is not able to absorb the earthquake energy, right? So you have to design your building in such a way that this should not happen, right? This should not happen. Don't make your structure brittle. You have to make your structure ductile, right? That is to be required. So the philosophy of earthquake resistant design, basically, I'm not going in depth as far as this philosophy is concerned, but I'm saying that damage is allowed. This is the only philosophy in which damage is allowed, but collapse is not allowed, right? Damage is allowed. So we are allowing damage. When the major earthquake will come, our structural element will absorb the damage, and after the earthquake, we have to retrofit our structural elements, and we have to make our structure functional, right? So again, if we go for the comparison of these two, again compare this to earthquake proof design. Earthquake proof design means we are designing our structure for the maximum expected force, and your structure should remain elastic throughout the earthquake, and if it remains elastic, then there is no damage. So it is safe, but it is uneconomical. But here ductility is not required. This is, but you are designing for very high force, high level of force, and you are making your structure uneconomical, and we are not sure whether your building is going to see earthquake or not. In earthquake resistant design, we are designed for certain level of expected force, right? And we are relying on inelastic deformation, right? We rely on inelastic deformation where damage is allowed, right? So when you are designing for 20% force, so definitely your structural element will be very small as compared to the 100 kilonewton force, right? So it is economical, and it is also safe because we are not allowing any sort of collapse. But here the most important thing is ductility is required. Remember, ductility is required, and IS 13920 is very important for earthquake resistant design. Now only important thing is, if earthquake comes, you have to be ready for the retrofitting in case of a major earthquake, right? Now our philosophy is saying that the collapse is not allowed. Collapse is not allowed, right? But what is the reality? What is the fact? The fact is structures are still collapsing during earthquake, right? If you look at a 1994 Northridge earthquake, 1995 Kobe, or 1999 Turkey earthquake, or 2001 Bhuj earthquake, we have seen devastation during these earthquakes. You see, Japan is considered to be the best as far as earthquake preparedness is concerned. And even though in 1995 Kobe earthquake, numbers of bridges were failed in Japan, right? And it exposes the wrong practice of uh, uh, earthquake resistant design, right? So even though Japan is very proactive, because Japan is sitting on ring of fire, and Japan has observed earthquakes at a regular interval. And even though this is happening with the Japan, then this is really alarming. If you look at the America also, in America, few, numbers of building collapsed, not like India or Turkey, but uh, in America, few buildings are collapsed as compared to the developing country like Turkey and India, right? But the structural failure had been observed during the strong motion, right? And what is happening? I told you the loss of life. Now, this kind of picture we always observe during the earthquake. If you see such kind of pictures, then these pictures will distract you as a civil engineer. You are or we are not ready to accept this, right? It always questions us, who is responsible for this, right? This is the picture from 2001 Bhuj earthquake. I want to share my experience of 2001 Bhuj earthquake. You see, I was working as an NCC officer, and we actually work with the Indian Armed Forces. Right now, Indian Armed Forces was given the responsibility of rescue and relief operation after the 2001 Bhuj earthquake. So what they have done, they have cordoned each and every collapse site, and they are bringing the dead bodies and valuables out of that out of that debris. Right? And our NCC cadets were working with them, and we worked for almost 6 months, and we learned a lot. Right? Our NCC cadets have brought the dead bodies out of the collapse site. I was also involved uh, in bringing a dead body of 4-year-old boy. Right now, we are bringing it out, it always questions in your mind as a civil engineer, who is responsible for this. I want to say that after bringing that dead body of 4-year-old boy, I was not able to sleep for a month. I tell you, right? And it always question us that who is responsible for this, right? As a civil engineer, we are not expecting this. If such thing is happening, it means someone has committed mistake, right? And who has committed mistake, it is very difficult to find out, right? If you look at the news uh, uh, news on this Sunday, that for the first time in Gujarat, the builder and the structure engineer is punished by the court, right, because of the low quality construction. This is the first case which punishes the builder and the structure engineer because of the poor quality of material. Right after 21 years, this I'm talking about the news of 4th June 2022. Right. So you see, as a civil engineer, someone is responsible uh, who committed mistake, and because of that, the structure collapsed. Right. So as a civil engineer, we don't want to see such kind of pictures. Because of this, the Anjar, Bachao, Rapar, this villages or town came to debris, right, during the 2001 Bhuj earthquake. If you look at this, the building collapsed, right? This is a typical soft story failure. So this is actually loss of property, and maybe a loss of life is also involved in such kind of collapse. If you look at this column is almost gone. Now this column don't have any capacity, right? So now you have to retrofit this column. Now the most important part is that even though this column don't have any capacity to take any load, if you look at this damage, definitely this column is not able to take any more load. And even though this structure is standing, it means the load of this column is taken by the neighboring column, right? But after this you have to retrofit it, and again you have to make your structure functional again. Now the health centers, hospital buildings are affected. Generally, when we design hospitals, we are designing hospital building as an important building, and we are designing for a 1.5 importance factor. It means we are designing for higher earthquake force, and we always believe that hospital building should remain functional after earthquake. And this is uh, the hospital building which collapsed in the Bhuj region. Now just imagine, in the Bhuj the earthquake was taken place, and this hospital building collapsed, and people were taking treatment in the open spaces. Now it was uh, winter, right? And the uh, um, uh, this should happen, right? If you look at the schools, 12,000 schools either damaged or collapsed. They are made up of prefabricated elements. The joint detailing was very poor. The heritage building, uh, actually, they suffered a lot, and we are knowing that this we are not able to restore this heritage building, right? Because we don't have the skilled manpower. So once heritage is lost, it is lost forever because of unavailability of the skilled manpower. This, you can see, this is a Mani Mandir in Morbi. It was damaged, and after 12 years, it was partially retrofitted, and people start using it again, but not the 100% portion is underutilization. This is the fort of Bhuj, damaged, and it is, again, I'm saying it's difficult. Lifeline structures are affected a lot. The bridges affected a lot. You can say roads network affected. So under these circumstances, we are not going to carry out rescue and relief operations. It is affected a lot. The electric power affected. Harbor structures absorbed a great damage during the 2001 Bhuj earthquake, and the industrial structures which are constructed with the RC elements, they have absorbed damage. The industrial structure constructed with the steel structures, they are not affected because they are a very lightweight structure, and but the RCC structures affected a lot because they have a larger span, and uh, they are very massive, and the economic loss is very difficult to estimate, right? So if you look at the 2001 Bhuj earthquake, almost we have lost 25,000 crore, right? Now if you consider it today, then maybe it is more than 4 lakh crores or 5 lakh crores, right? So it is the loss or economic loss, it is very difficult to estimate, right? So uh, the challenge number 4 is the construction practice. As the structures are still collapsing during earthquake, someone from the construction industry is or are responsible for this disaster. And who are the stakeholders of the construction industry? We are knowing the builder and owner, right? Who is conceiving the project? He must be honest. If he's not honest, then definitely we are adding unsafe structures. Architect has to give good configuration. Structure engineer has to impart the structural safety. Site engineer has to look at the quality of construction, right? The mesh and carpenter has to look at the quality of construction. The authority has to enforce the law, right? And if we enforce the law properly, then uh, all the stakeholders of the construction industry will follow that, and definitely we have a much better uh, structures in the society. And the teachers and students, uh, they are part of capacity building part, right now the this training is organized, and basically we are building the capacity in the area of earthquake engineering, right? So these are the various stakeholders, and what attributes we want from this, it is marked against them. The challenge number 5 is the error in safe construction, right? So generally we are committing 3 types of mistakes uh, during the construction. There's an error of intention, error of concept, and error of execution, right? Now the error of intention means what? The error of intention means I'm knowing that what is the wrong practice, right? And uh, I don't want to go for the correct practice. I want to I'm following the wrong practice, even though I'm knowing the correct practice. So that will is considered under the error of intention. Error of concept. And what is the error of execution? The error of concept means you are knowing that there is earthquake resistant design, but you are committing certain mistakes in earthquake resistant design, right? For example, you are not going for the ductile terrain, even though you are knowing that. So that is the error of concept. And error of execution means, for example, structural engineers are providing the drawing on site, and the structural engineer has provided a good ductile terrain, but it is not executed on site properly, or quality of construction, it is not maintained on site. So that is the error of execution. And out of these three, I tell you, the error of intention is the worst error. Suppose if you are knowing that how can you make your structures safe, and you are not making your structure safe, that is the biggest error we are making, right? So you cannot handle then this error of intention. It is only the comes under the punishing those people who are committing this mistake, because they are knowing but they are not following, right? So generally the error of intention is not there. It is not our intention that we are going to construct a 30-story building, and then I feel that okay, if this 30-story will collapse and then this many people die, I'm happy. No. So generally most of the time we are not committing this error of intention, but as a civil engineer we are committing these two mistakes: error of concept and error of execution. Error of concept means if earthquake engineering is not taught at the undergraduate level, earthquake resistant design is not taught at the undergraduate level, and then what is going to happen? The civil engineer is not knowing what is earthquake resistant design. So if he is doing a side practice, then he is not knowing earthquake resistant design, so it is not going to implement it. So that is the error of concept, right? So the error of concept is the next level of mistake, and error of execution is generally we are committing error of execution, like we are not maintaining the quality quality of construction, or we are not executing the correct structural design on site, right? So out of this, error of intention is the worst, then error of concept, and then error of execution, right? So generally these three errors we are committing, and they are very very dangerous for the safe construction, right? Now the next challenge is a change in the attitude. Change in attitude. What is the change in attitude? It's a mode of denial. Okay, we will take the case of 2001 Bhuj earthquake, right? This earthquake is having magnitude 7.7. 1,805 people died. It is as per the official record of the government, I tell you, right? Now, if you imagine about the Ahmedabad, the Ahmedabad is located almost 250 kilometers away from the epicenter, right? 130 multi-story building collapsed. They are ground plus 4-story, right? Most of the buildings are ground plus 4-story, and two buildings they are ground plus 10-story, Mansi and Sikhar. Almost 805 people killed in 70 buildings, right? Out of this 130 buildings collapsed, in 70 buildings 805 people died. Now if you look at this buildings, then you find that these buildings were very new. Life is less than 10 years, almost 10 years, right? They are designed by the architect and engineer, built by the developers. And if you look at the buildings of old Ahmedabad, in old Ahmedabad, like we are talking about the old construction like pole, right? So we have not seen the collapses of those old buildings, right? Now this is the collapse of Mansi building. Is a ground plus 10-story building in Ahmedabad which collapsed. There are two buildings, Mansi and Sikhar. They are 10-story, 11-story building. They are collapsed during the earthquake, right? Now, uh, what was the argument of the structure engineer and builder? They are saying that this earthquake was very unusual earthquake. This earthquake was very unusual. The intensity what we felt at Ahmedabad was above, or it is more than the expected in Ahmedabad. But fortunately, we have a broadband seismometer in the passport office in Ahmedabad, and we have a record of earthquake in the that broadband seismometer. And you see, Ahmedabad is in zone 3, and therefore uh, as per the as per the Indian code, as per the Indian code, the intensity which is expected is 7. Intensity 7 we are expecting, and the maximum intensity observed during the Bhuj earthquake was 7. So it was not an unusual strong shaking, right? If you look at the Bhuj is in zone 5, so we are expecting intensity more than 9, and the intensity in Bhuj was 10. So again, it is within the limit as per the code. So we are in a mode of denial, right? But what are the reasons why this happened in Ahmedabad? It is because of the total disregard to the structural system. The structural systems were not proper. You see, even if you talk about the lift, right? Generally, the lift well is constructed with the RCC, and in this building, many of buildings we have seen uh, this lift well constructed with the masonry, right? That is a so. I think this is a very poor practice. The structural system is very irregular. We have a soft story, we have a parking at the ground story, right? And then we start living on the upper story. So what is happening? The ground floor will become very soft, and almost 90% building in the Ahmedabad which were collapsed, it is because of the soft story. We have not followed the structural design principles. The quality of construction was very poor. And you see, I tell you, there was a building in Junagadh. It was a 10-story building, and this 10-story building was collapsed not during the earthquake. Normal, it collapsed under the gravity load, right? So you see, this type of poor quality of construction, right, which is lead to the disaster, big disaster, right? Now the question is like developed country and developing country, right? If uh, I told you that in Bhuj in 2001 Bhuj earthquake, 13,805 people died, right? The similar earthquake was taken place in California, and how many deaths had been observed? There are 50 deaths in California, right? America is a developed country, and they have a very strict and stringent bylaws as far as earthquake safety is concerned, right? So they are strictly following that. So enforcement by the authority is really wonderful in America, but still buildings are collapsing in America, right? If you look at India, in Latur, 1993 Latur, almost 8,000 deaths had been observed. In Kashmir, 2005, 95,000 deaths had been observed, right? So if you talk about Iran, Turkey, or Pakistan, uh, you see, if the earthquake will take place, then thousands of people will die. If you look at the economic loss, then I told you that 25,000 crore, the 5 billion US dollars, right? That was a loss. If similar earthquake, this earthquake was taken place in Bhuj, if similar earthquake taken place in north or northeast boundary, then it will be more expensive. Now, the another challenge is we are not learning from the past earthquake. We are not learning from the past earthquake, right? I'm just discussing a few examples of it. Uh, 1 minute. If you look at the Bihar Nepal earthquake of 1934, right, intensity was 8.4. Sorry, magnitude was 8.4. Intensity was 10 on modified Mercalli scale, and almost more than 10,000 deaths had been observed. 11,000, right? Death had been observed. Now, question will arise: that no such big earthquake taken place in this particular region? Then answer is no. There was a big earthquake in 1833 also, 1833, right? And we haven't learned from this. And after almost 100 years, another big earthquake hits the Bihar, Nepal, and we have seen such a casualty. So we are not learning from the past earthquake. That is the problem, right? That is the problem. Then, if you look at the the second part, right? The second example I'm giving you. For example, a Bhuj earthquake, 2001, 7.7 magnitude, intensity 10 on Mercalli said, that is the observed, death 13,805. Now, question is, was Bhuj earthquake a first earthquake to hit urban region? Then question is no. We had an earthquake in 1997 Jabalpur, right? 1997 Jabalpur. Jabalpur is a city like Ahmedabad, and the urban area is affected. Urban area is affected. But we haven't learned. You see, we have seen similar type of failures in Jabalpur earthquake, but we have not learned from Jabalpur earthquake. Why? What is the reason? The reason is the magnitude of that earthquake is 6, and number of deaths were only 38, right? So we have a country of 135 crores, and after 135 crores, only 38 people died. Right. Now, this 38 people die by any means, I tell you. So we are not taking it seriously. If you have learned something from this Jabalpur earthquake, we might have saved the Ahmedabad, right? But we haven't learned from this earthquake. Now we talk about, we are talking very negatively. You feel that, right? But there are some positive stories, success stories from India. We have seen, yeah. But it is a long time back, right? 1930 in Balochistan, 1897 Assam, 19th century Srinagar in Kashmir. So these are the three main examples from where we can learn something, right? So we are talking about the early development on safe construction. You see, this is the Dhaji Diwari construction. Dhaji Diwari construction in Kashmir, right, in Srinagar. It is developed after the damaging earthquakes in 19th century, right? So what they are doing, there is a masonry structure, and this masonry structure is associated with the wooden bamboo, and it work as a bracing, right? This work as a bracing. So this work as a bracing, and performance was excellent, right? So this is not designed by the engineer, I tell you. This structure is designed by the people of Kashmir, people of Srinagar, and they learn from the past earthquake. They learn from their experience. If you look at the 1897 Assam earthquake, the Assam earthquake is considered one of the greatest earthquake of the world. If you look at the mean radius of perception is 900 miles, and the mean radius of serious damage was 300 miles, 450 kilometers. This is the radius where the serious damage had been observed. And the longest dimension of the mesoseismal area is 160 miles. Right? So this 160 miles has observed a tremendous damage. And this is the earthquake where for the first time we have seen the acceleration is more than 1G. More than 1G. Right? It means the stones which are lying on the earth, they are moving in the upward direction. Right? We have seen a liquefaction in the alluvial plain of the Brahmaputra. Right? Now, you see, when the stones are thrown upward, it means the vertical acceleration. The vertical acceleration is more than 1G. Right? Because we know the gravitational acceleration is 9.81 meter per second square. And if the stones are moving in the upward direction, it means the vertical acceleration is more than 9.81 meter per second square. And after this earthquake, you see, up to 1897, there are only 10 scales as far as the Mercalli scale of intensity is concerned. But after the Assam earthquake, two more scales had been introduced, and now we have a, modified Mercalli scale up to 12. That comes after the Assam earthquake, right? And you see, after the great earthquake of 1897, this ICRA type of housing or construction is developed in the Sikkim. Right now, what they are doing, they are constructing the houses with the stone and bricks up to the plinth level, and after that, they are constructing. They are introducing the wooden element. This wood is very ductile in nature, and it is also lightweight as far as the mass is concerned, right? So this ICRA type of housing comes in picture in Sikkim after 1897 earthquake. But currently, again I'm saying, currently these houses are replaced by the poorly constructed RC and masonry building. If the big earthquake will come in Assam, then again we'll see a large casualty in Assam. The best example of the success story of India came from the Balochistan, right? In 1931 March, there was an earthquake whose magnitude of 7.4 in Balochistan. The intensity 8 was observed. 100 people died. Now, this earthquake has raised a concern for the safe houses for the railway officers, right? So the SL Kumar, he is a very young engineer. The age was 28 years, and he was given responsibility that you design houses for the railways, and he has done a lot of work to make this railway quarters, to make them earthquake resistant. Right. So in 1933, the Kumar has presented a paper, and he has given a concept of earthquake resistant construction. Detail of his design and cost implication. The first ever seismic zone map of India he has given, and he has given a seismic coefficient for the two types of building, right? And this is the seismic zone map given by the SL Kumar, right? So again, I'm saying there was an earthquake in 1931. It was 7.4, and 100 people died. And after that, SL Kumar was given the responsibility to construct the railway quarters. And there was an earthquake in 1935. It's a Quetta. The magnitude was 7.6. Intensity observed was 10, maximum intensity. 30,000 people died. 40% population. Remember, 30,000 people died during the Quetta earthquake. But the quarters or the railway quarters which are designed by the SL Kumar performed excellent, right? And you see, SL Kumar has not learned earthquake engineering. He has designed everything by understanding the structural behavior. What he has done, this is okay. First, look at this picture. This is the picture where this quarters. This is the picture from the Quetta. These buildings collapsed, but these buildings absolutely safe, right? Designed by the engineer SL Kumar, right? Now, what he has done, he has introduced a masonry in which he has introduced the reinforcement, right? He's knowing that masonry is a brittle material, right? The failure of the masonry structure is very brittle, and when the lateral force is acting, these masonry structures are very vulnerable. So to take the tension, he has introduced the reinforcement, and he has created a bond. Like we have an English bond, we have Flemish bond, but he has introduced a new type of bond in which he can introduce the reinforcement, and it is known as a Quetta bond. You see, Ashal Kumar has not learned any earthquake engineering, but he has designed this building on his knowledge only, right? And these structures have performed excellently well during the earthquake of 1935, right? So it gives us idea that if you do anything honestly and anything for the society, you can do wonders, right? So we are knowing that some fantastic work has been done after 1897 to 1935, right? New typology of the buildings were introduced, the Quetta bond, Assam type of housing, the Ji Diwari. But after that, after 1935, there are many earthquakes, but we we have not done anything. If you look at right now, we are more vulnerable than 50 years ago, right? And another important thing is the development in 1897 and 1935 were led by the professionals, not by the academicians, right? So it should be, means academics should have to lead this. Instead of that, the professionals were leading at that particular moment. So there is a new possible construction typology in India, is a confined masonry, for which we are conducting this course, and we will learn many things as far as confined masonry is concerned. The another important thing is a challenge. Another challenge is the content of the code, right? We have IS 875, right? There are 5 parts. The first is dead load, superimposed load, wind load. Fourth is a snow load, and the fifth is a load combination. But as far as the seismic load is concerned, we are creating a separate code, IS 1893. So it must be included in IS 875 itself, because earthquake is a similar type of load, right? And this load you have to consider. So people are knowing 875, but people are not knowing IS 1893 before 2001 in Gujarat. This was happened. We have asked many people; they are not knowing even 1893. So this is something unusual. So this IS 1893 should be a part of IS 875. It should be. There are 6 parts. The first is dead load, second is superimposed, third is wind, fourth is the earthquake, fifth is the snow, and then load combination. That is fine, but it must be included in here only. The second challenge was the regularity in development of the code, right? The IS 1893 is the code for earthquake resistant design. It was developed in 1962, right? And then it was revised in 66, then 70, means after 4 years, then 5 years. After 75, it was again revised in 1984 after 10 years, and then 1984 to 2002, right? After 20 years, and now it is in 2016. So after 14 years. So this revision should be regular at the interval of 3, 4, 5 years, right? Now, if you look at the biggest revision we made in 2002, right? Now look at how this code came in picture. There was an earthquake in Latur in 1993, so the revision was started. Revision of IS 1993 was started, and this was revised in 2002, means after the 2001 Bhuj earthquake. So you understand, we need one earthquake to start revision, and we need another earthquake to complete the revision, right? So this should not happen. The code must be revised at an interval of 4 or 5 years, right? We have to include. We don't want landscape changes in the code, right? We have to include the latest practice in the code. That is required. So we are not doing at a regular interval, and you see, very few people are contributing as far as the development of this code is concerned, right? Few people. So many professionals, many academicians should have contributed, or should contribute in the development of the code, right? Uh, we have a IS 13920, right? Because in 1993, now it was the code of ductile detailing only, right? Ductile detailing, and almost after how many years? Almost 23 years. After 23 years, we have a revised IS 13920, and where a ductile design is available now. Now, still we have many questions, but a new code came in 2016. It is quite good, and I think if we follow, we can have a good design. We need an improvement in the research. That is again a challenge. If you look at this, I'll give you a simple example. Right? The Latur was hit by a major earthquake in 1993, and at that moment the Latur was in zone 1. And after the earthquake, the Latur was immediately placed in zone 4. Right. So this should not happen. This should not happen. This seismic zonation of India should be based on the scientific research. Right. For example, the ISR, Indian Seismological Research Institute, is doing a microzonation of the Gujarat. They have completed microzonation of Kutch region. They have done it in the Gandhinagar also, in Ahmedabad, and the many other parts of the Gujarat. Right, and it is a scientific basis to have a seismic zoning in India. But if you look at the other part of this map, no scientific research. Means at few places it is taken up, but not at the most of the places. So it should be based on a good scientific research. Now, if you look at the some headlines in Delhi, right, regarding the earthquake safety, government withdraws order for safety certificates. Government has said that the structural engineers or the competent people have to issue the safety certificate to the buildings, but they have withdrawn their orders. Because what is the reason? There are no structural engineers, so no safety certificates. So we don't have the enough number of good structural engineers who can say the structures are safe or not. Right? That was the structure certificate a problem. Remove clause MCD to government. Who will issue the safety certificates? Right. So these are the problem with the human resources. You see, I'm telling you another way. Suppose if you are going for a plan passing, right? So what we do, the plan is prepared by the architect. Now he is submitting the plan to the authority, and then authority will check the plan whether it is as per the GDCR or not, and they are looking at the FSI, right? If FSI is 1, suppose there's a 1,000 square yard plot we have, FSI is 1, then they look at the construction. If it is a 1,000 square yard, they are approving, right? And then once the plan is approved, this plan go to the structure engineer. Structure engineer will design, and then he will submit the design and the drawings to the authority. Now this structure engineer is, when submitting, now these drawings and designs are not checked by anyone at the or by the authority. The reason is they don't have the enough manpower in form of structural engineers. So what they say that, okay, anything will happen, it is a responsibility of structural engineer, right? If any wrong practice is followed, because the structure engineer is signing everything, is drawings and design, right? So we don't have the enough human manpower in form of structure engineers, and also for the controlling the quality on site, right? Earthquake engineering is always projected as a super specialty. Now it should not be, right? Professionals not actively engaged in the agenda and the single institution model for too long. For example, IIT Roorkee. The IIT Roorkee was dominating for so many years, and they are talking about the earthquake safety. But you see, if you want to make the whole India earthquake safe, then the single institution model will not work, and we have to train everyone from the construction industry. We must have a good enforcement framework for the code compliance, right? So we must have certain incentives, at the same time certain punishment, right? For example, if uh, if you are not wearing helmet on two-wheeler, we are punished. If we are not wearing we are not wearing the seat belt again in the cars, definitely we are punished, right? So such kind of incentive and punishment should be there for uh, wrong design or the correct design, right? There must have been legal clarity on the code enforcement. uh, this is another important thing, licensing of the structural engineers, right? This is very important, right? How we uh, allow civil engineer to design the structure. It is not based on the knowledge, it is based on his experience or her experience, right? If someone is graduating and he must have a correct knowledge, right? Then and then he should design. The municipal authorities have to ensure the compliance at the time of building permit and occupancy, right? That is to be required. So municipal engineers to ensure the drawing comply, the develop system for on-site inspections. Structural engineer professions to be regulated through the engineers bill. Right? This is very important, and we don't have the engineers bill. We, you see, on-site, we are knowing that the role of the mason is very important, right? The masonry work from for earthquake resistance is something different, and if the mason is not doing good masonry work, then we are allowing troubles. So certification of masons or bar bender is required. We have done for 3-4 years, but after that again we stopped, right? Because we forget the 2001 earthquake and we stopped it. I told you the competence-based licensing of engineers is required. So Gujarat Council for Professional Civil Engineers, this act was passed in 2006, and now in 2022 they have implemented it, and they make it compulsory for all the engineers to appear in the exam, and they have to clear the exam for the practice. So general engineers, general civil engineers, if they want to do practice, then they have to pass the exam, which will be taken by the Gujarat Council for Professional Civil Engineers. If they want to work as a structural engineer, there is a separate exam, and they have to appear in that exam. That is required. Right? What other things are required? The peer review on important projects. So, like right now, any government projects, they are going for the always peer review of this project. The structural documentation is necessary, right? And the sample checking of drawings and construction, uh, just like the case of income tax return, right? So, if you look at the major earthquakes, these major earthquakes are giving us a window of opportunity to to go for the changes, uh, in the construction field, to go for the capacity building, right? But this window is very short and often wasted, right? In 2001 earthquake came in Gujarat. We are very serious for 2001 to 2009 or 10, and after that, again, everything is diluted. The earthquake engineering subject was introduced as a compulsory subject in 2003, and in 2016 it was made elective, right? So you see, before 2001, this subject was not taught at an undergraduate level, and when a high committee has find out the reasons for the devastation, the one of the reason was that this subject is not taught at the undergraduate level. That was a major reason for the devastation. And then this subject was introduced, and in 2016 again people start forgetting earthquake, and they have removed this subject. I think the people from universities, the professors, the academicians, they have removed the subject, and they have placed the subject in the elective. And right now 10 to 12,000 civil engineers are graduating every year, and out of this 10 to 12,000 civil engineers, only 500 or 600 students are taking this particular subject, right? So we are not serious about it. So we must have a roadmap. We know that we have discussed this, that the theory of seismic gaps and this blue region, these are the potential region where a big earthquake may come, and we have to ready for that. Right? We know that the earthquakes are occurring at a regular interval, and a mega earthquake disaster awaits India, particularly in the north or northeast boundary, Indo-Gangetic plains. So we are knowing that this is very important. Most of the construction are generally deficient in the particular region, right? And therefore we have to work a lot, and we know that solution lies in the building, not in the earthquake. So we need a urgent intervention of the building industry that is to be required. I told you the earthquake safety is a long and hard struggle. You will not get an instant result. All right, like CNG campaign. I had given you example that California started earthquake safety program in 70 years back, and still it is going on. Right, it is still going on. So India has not started yet, and so how much time we need, I think it is we cannot say right now. Certain initiatives were taken in Gujarat after 2001 earthquake. I'm saying that the curricula of civil engineering, the earthquake subject was introduced, but it was removed in 2016. Training of engineering teachers were taken place. Training of engineers were practicing, and government engineers were taken place. Awareness regarding the building taken place. Mission training and certification was started. Seismic microresolution had been done. Seismic codes were developed by IIT Kanpur and GSDMA. Two good organizations came up in Gujarat, is a Gujarat State Disaster Management Authority and Institute of Seismological Research. And the most important thing is the Gujarat Council for Professional Civil Engineers was formed, and Gujarat Professional Civil Engineering Act came in 2016, but it was not implemented up to 2021. It is now implemented in 2022, right? And now this council become very active, and they start taking the examination, and now the certification will be based on knowledge, not on experience. So what is remaining remaining as far as initiatives are concerned? Basically, we have we are knowing that the GSDM and ISR came in picture, but no technical institution which came up to deal with the problem of unsafe construction. It is not, so that is the problem. So the roadmap to seismic safety, basically community awareness. We have to spread the awareness among the people, and when they purchase the houses, exactly what they have to see. Right now, we are not talking about, suppose if I am purchasing my house, I am not looking at the structural safety. I am talking about the aesthetics of that building and the cost. These two parts I am observing, and that's enough for me. But we have to create awareness. We have to create a legal framework. We have to create technical competence, professional ambience, enforcement by the local authority, and research and development. So we have to focus on these areas. This is the roadmap to the seismic safety. There are three factors which lead to the great disaster: an earthquake of sufficiently large magnitude, sufficiently small distance from the fault, and a city or region with a sufficiently weak buildings. Right? I'm talking about the Great Tungashan earthquake of 1976. Magnitude was 7.8. 243,000 people died out of 10 lakh. What is the reason? The fault was passing through the city. We have a fault below Chandigarh city, but it is not active. So we are lucky that it is not active. But this fault in Tungashan was active, and 25% people died. 25%, which is remarkable. Buildings are not designed to resist earthquake. This earthquake was, I tell you, 7.8 magnitude, Tungashan earthquake. But if you look at the city of Agadir, Morocco, this city was struck by the earthquake of 5.7 only, right? And 10,000 people died out of 30,000. 1/3 population is gone, right? What is the reason? The buildings were weak and brittle. Now, great disaster don't require a large city. Imagine, suppose this will happen in Mumbai, what will happen, right? So, what can we do? We cannot predict earthquake or stop earthquake event to happen, but we can prevent a collapse of structures by adopting good technology and good practice, right? This is in our hand. We cannot predict earthquake or stop earthquake event to happen, but we can prevent collapse of the structures by adopting good technology and good practice. What can we do? We design and construct a new structures to perform satisfactorily during the earthquake. We can address the problem raised by the weak old structures. And who can do that? The engineers and authority, right? Engineer authority, they are the primarily responsible for this. Factors for the good seismic performance. We have not discussed the technical part right now. So basically the configuration, lateral stance, stiffness, ductility, action, integral action, quality of construction. This is to be required, right? We'll discuss later on this part. So we are always saying that seismic design is a shared architectural and engineering responsibility. If architect and engineer they are working separately, then for the case of earthquake, then they are inviting disaster, right? If they work separately for the gravity load, that is fine. But if they work separately for earthquake effects, then they are inviting trouble, they are inviting disaster. So architect and structure engineers to work together, and good interaction is required between architect and the structural engineer, which is very important, which is missing right now. I tell you, in India, the interaction between the architect and structural engineer and civil engineer is missing. And this is the example, right, of the teamwork. If architect and engineer is not working together for earthquake, this is going to happen, right? Everything will be messed up at the end. How much we have learned? This is a very important cycle we learned. When a big earthquake comes, you see, time-wise we try to understand. For any major earthquake, there are positive reactions and negative reactions, right? So we'll look at some positive things are taken place and some negative things are taken place. So if we're talking about the first minute of the major earthquake, there is a panic, right? Because collapses and damages had been observed, and people are afraid. 1 minute to 1 minute. Still, people have a fear in the mind that next or aftershock or big earthquake, next big earthquake will come. We don't know. 1 month to 1 week to 1 month, aftershock is reducing. So short-term repair started. But what is the negative thing? Now people are coming out of the shock, and they start blaming the builders, designers, and officials. 1 month to 1 year, long-term repairs, action for the higher standards, that is going to take place. 1 year to 10 years, our interest is reducing. This is what we observed in after Bhuj earthquake. You see, we introduced earthquake engineering subject, and then we start removing the subject from the curriculum, right? And now it will become elective. So our interest is reducing. 10 years to next earthquake, we are reluctant to build the cost of the seismic provisions, and then the next earthquake will come, and again the same steps will be repeated. So this is the cycle observed all over the world, not only in India, but is observed in the world. If we are encashing this thing, if we learn from the earthquake, then definitely it is a positive for that particular country. Why I place this picture? I place this picture because he is a Ghazni, and he is known for loss of memory, and we are sailing in the same type of the boat. We are not remembering earthquake for a longer period, and that creates a lot of problem, right? So what is the conclusion for safety in future earthquakes? Simple. All provision of the code should be followed in design and construction, and this should be mandatory provision in the building bylaws. That's all. We have to follow the codes. That's all. This is the only requirement. And we are always saying that pay a little now. So we have to pay a little attention now. Otherwise, we are going to pay a lot later. Right. So that is there. Your time is already started, and we have to begin with the end in the mind, because we are knowing that earthquake journey for earthquake safety is a very long journey, and uh, we have to work hard. We don't know how much time we need, right? So let us prepare ourselves to reduce earthquake to a nuisance rather than a danger, and convert the earthquake disaster into a routine event. That is required. So this is the last statement by the Henry Degenkolb, who is a well-known structure engineer of California. You just read out, because this is very important. Just read this statement by Henry Degenkolb. Some of us used to argue that you shouldn't really get your structural license until you have chased an earthquake. No matter how much you read the reports, the impact doesn't really strike you until you have seen the damage and casualty. I tell you, I have the same experience after 2001 earthquake. I was teaching this subject before 2001, but I become very serious after 2001. Right. If you are reading the reports and everything, but definitely uh, uh, it will not give that impact. But if you have seen that casualty, right, then you are never going to forget that casualty. Still, I remember the dead body of that 4-year-old boy. Right. So uh, this is a wonderful statement made by Henry Degenkolb. Again, you have to read this, you have to understand this, and you have to implement in your life. That is to be required. So if you have any questions, you can ask. Uh, this is from my side as far as my session is concerned. Thank you. Any questions? Any questions?
All the participants are requested to ask the questions if the house is now for the question. They can raise their hand and unmute themselves.
If you have any question, please ask. You can write in the chat box also. Yes, please. Aditya.
Yes, sir. I guess there are no questions from the participants. If at all you feel any doubt or any questions, you can post your questions in the WhatsApp group as well. Our speakers and experts will look at your question and answer. And in upcoming sessions by our speaker, if you have any doubt, you can raise your hand and ask the question. So yes, sir, it was quite an amazing session as always, quite informative, and I would say an eye opener for all the civil engineering professionals and the students who are participating in this program. That how lethal and destructive an earthquake can be, and what challenges it can impose. I'm pretty sure that all the participants would determiningly look forward to work in innovative practices like confined machinery to develop our structures better so that they can perform well in the situations like earthquake.
Yes. Thank you. Thank you very much. And my special thanks to Dr. S.K. Jain, who is Vice Chancellor of BHU, and Dr. C.V.R. Murthy uh, for their contribution in the area of earthquake engineering, Dr. Svetlana Braze, and many. So here we are ending the session 3, and before that we want to pass on certain information. First of all, as far as the program is concerned, at least 80% attendance is required, and at the same time we are going to conduct a quiz at the end of the program, and you have to score minimum 50% marks. So this is the criteria for getting the certificate, and we are going to give you the assignment, and this one assignment, that is design part, you have to submit in a stipulated time. So that is to be required, and we are basically going to give you the certain resource material for the reference. You can refer that, and I hope you will interact with the faculty members to the best extent, and you get this opportunity to understand the concept of confined machinery. So we are going to share the assignment also, and our quiz, it will be based on the topics of this program only, right? So be prepared for the quiz also. This is thank you. This is from my side. Thank you very much.
Thank you, sir. Thank you. So once again, all the participants are requested to take note of all the information which sir have passed, and also all the materials and the codes which are shared on WhatsApp group. You can take and refer those publications from our WhatsApp group. And a gentle reminder that tomorrow first session again we will be starting at morning 10 a.m. It will be taken once again by Dr. Svetlana Brizev ma'am, and the topic will be machinery materials and design methods. So you all are kindly requested to join on time and enjoy the session. So that's it. I guess we can end here.
I think we have a certain official from IIT Kharagpur.
Yes, sir. Yes.
Hello.
Yes, sir. Yes, sir.
Sanghvi sir.
Yes.
This is Hamil. Actually, I am lecturer in Bharuch College, Government Polytechnic. I have one question regarding the earthquake side. Actually, my question is that suppose I want. Hello. Am I audible, sir? Hello.
Yes, you are audible, but you are. I think you have two instruments, so lot of noise is coming.
Hello.
Yes.
Okay.
Yes.
Hello. Now.
Audible. Yeah. Audible. Yeah.
Actually, my question is that suppose I want to analyze the building against earthquake load. So we have numbers of analysis in terms of linear static analysis, linear dynamic, non-linear static, and non-linear dynamic analysis. So suppose to say I want to analyze the building which is in the zone 3. Suppose in Ahmedabad city there is a building and I want to analyze. So for non-linear dynamic analysis, suppose I'm choosing, and I want to analyze that building against various ground motions. So how to select the various ground motions to analyze that building, sir?
You see, if you look at the buildings,
Okay.
then these buildings are ranging from low rise to high rise. So this low rise building is having a high frequency, and high-rise building has a low frequency, right?
Yes, sir.
So basically, if you want to catch the response of this high-rise and low-rise building, then you have to take the earthquakes which contain high frequency and low frequency both, right? Suppose
Yes,
if I am analyzing a low-rise building, I'm knowing that it is the frequency of low-rise is high as compared to high-rise building, right? And therefore, if I am taking earthquake time history which contained a high frequency, then definitely the response of your structure will be high. Okay, because the frequency are close to each other. I'm not saying resonance is going to take place, because earthquake carries different frequency, so resonance is not possible. But if the frequency is close, then you get a higher response and you can have a better idea. For example, if it is a low-rise building and uh, I'm knowing that this low-rise building having a high frequency, and I'm considering the Mexico City earthquake, for example, right? It is a very low frequency earthquake. Then your building is not going to respond to that level, right? So you get a response, very low response, right?
Yes,
But
sir.
but if you use the like a Bush time history, then definitely this building is going to give you a higher response. So we have to take all sort of earthquakes possibly to to tap the response, and we have to create a response spectra, and we have to take the highest response, and we have to consider the highest response for the further design and analysis, right?
Okay, right, sir. Clear. And another thing is what that the how many ground motions that I have to consider to generate the response spectra, sir? Is there any
You see,
criteria regarding that?
if you look at the response spectra, what is there in the Indian code, there are thousands of earthquakes taken up, right?
Yes, sir.
And
Yes, sir.
after taking the so many buildings and numbers of time histories, they created this response spectra, so that everything comes under this spectra. So you see, I'm not saying any limit to it, but at least you have to consider significant numbers of earthquakes, so that you have a good data to come to the conclusion, right? So that is to be required. Maybe first of all, you have to understand the behavior of a structure, and then correspondingly you have to, if you consider 8 to 10 time history for the analysis, I think that will be sufficient for the normal case, right?
Actually, I refer that FEMA, and it is clearly mentioned that the 7 time histories you can take, you have 3 time histories you can take. When you are considering the 3 time histories, then you have to consider the maximum response from that. And if you are taking the 7 or more than 7 time histories, then you have to take the average of that response. So,
Yes.
is there any thumb rule or any criteria, particularly in our code or in our
No, no,
Indian
no,
side?
no, 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 no,
Okay,
no.
okay, okay.
Hmm.
Okay, thank you, sir. Thank you very much for your giving me the so clear answer. Thank you, sir. Thank you.
Thank you. uh, Anyone else? I think we have a person. Yes. Anyone else? We have the faculty members from IIT Kharagpur also. Sir, if you want to interact, please, from the Gyan office. Okay. Aditya?
Yes, sir. Yes.
Sir,
Yes.
I'm Aegean. Sir, I want to give some instruction to the participant.
Yes. Yes, Ashwin.
So, for the attendance, I will share one Google form, and in this Google form, you have to share your name with which you have joined this link of the session. So as on the screen, you can see the display name. So the name with which you have joined this meet, you have to mention this name in the Google form for the attendance. Okay, Google form with you in the WhatsApp group, and you have to mention this display name in that Google form, and we will manage the attendance accordingly. So that's it from my side.
Okay.
Okay.
So here, I think we'll close this meet and we'll meet tomorrow morning sharp at 10. Dr. Svetlana Brezev is